Hello everybody. First of all, I would like to thank the organizers, Sergey, Einar, and David, and Kititat, and Dan for inviting me to give this talk. I'm very happy to have this opportunity. This conference series on permutation patterns is by far my favorite conference, so it is really a pleasure for me to have the opportunity to present some of my more recent results that have been obtained in the last couple of years. Also, I would like to point out that all the results that I'm going to talk about have been obtained in collaboration with some people that you can see listed on this first slide. The first two of them, Giulio Cerbai and Lapo Cioni, are two PhD students of mine. Giulio has just finished his PhD and Lapo is in his second year. The other two guys I guess you all know very well, Anders and Einar. The collaboration with all of them has been absolutely fundamental in order to obtain all the results that I'm presenting. However, let me mention in particular the great job done by Giulio and Lapo, which, as I said, are PhD students, so at the beginning of their academic career. Nevertheless, they have worked really great, and their contribution has been fantastic, and it has been a pleasure to work with them. And I hope we can continue working together in the future, of course. So the main theme of my talk is sorting with stacks and queues, or more specifically, sorting permutations using stacks and queues. This is a very classical topic in the realm of permutation patterns, and certainly one of the main responsible of the development of the whole subject. The general framework for this kind of problems can be described as follows. There is an input permutation, say pi, and we want to sort it to obtain the identity permutation. To this aim, we have a machine that can be as simple as a single container, like a stack or a queue or anything of this kind, or maybe several devices connected in some way, for instance, in series or in parallel, or maybe in some more complicated way. So in general, we have a network of devices to try to sort our input permutation, and then we have an output permutation, which hopefully is the identity permutation, if our machine is able to sort pi. Otherwise, we wish to obtain an output permutation that, well, is somehow closer to the identity than the original permutation, whatever this can mean. It is useful to have machines that, even when they are not able to sort a given permutation, nevertheless they return some output. In this way, we always have a map associated with each of these sorting machines, which could be interesting to investigate. There are several interesting questions that can arise in the study of these sorting machines. Here I have listed the three main ones, at least in my opinion, or at least certainly three of the most important ones. From the point of view of the combinatoriality, it is interesting to find a characterization in terms of pattern avoidance, or a geometric characterization, or whatever, and the enumeration of those permutations that are sortable by a given machine. From the point of view of the computer scientist, an interesting problem is that of finding some optimal sorting algorithm, that is an algorithm which is able to sort all sortable permutations. And, well, from the point of view of the mathematician in general, it is important to investigate properties of the sorting map associated with a given sorting machine. For instance, one could try to understand preimages of a sorting map, which is in some sense a generalization of the first question, since in fact sortable permutations are precisely the preimages of the identity permutations. In my talk, I'll give three types of results, one for each of the above three main problems. I'll start by illustrating an optimal sorting algorithm for a certain sorting machine. Then I will introduce a new family of sorting devices, and I will address the problem of the characterization and enumeration of the sortable permutation. And finally, I will consider a, well, rather simple sorting machine, and I'll describe some results concerning preimages of the associated sorting operator. Before starting, just a few words about the history of the subject. The first of these kind of sorting machines for permutation was that consisting of a single stack. So we have an input permutation, usually depicted on the right in this framework, and we want an output permutation, usually on the left, and in the middle we have a stack. There are two possible operations that we can perform. Either we can push the current element of the input into the stack, or we can pop the stack and put the top of the stack into the first available slot in the output. So for instance, we can consider this permutation here, and the first thing that we can do, of course, is just to push the 3 into the stack. And now we are already in trouble, because if we choose to pop the stack and place the 3 in the output, then of course the resulting permutation won't be the identity. And if we decide to push the 6 into the stack, then the 6 will reach the output before the 3. So again, the output permutation won't be the identity. However, what we can do is to design an optimal sorting algorithm by simply observing two crucial facts. First observation is that it is convenient at each step of the sorting procedure that the content of the stack is increasing from top to bottom. And the second observation is that at each step of the sorting procedure, it is convenient to push the current element of the input into the stack, of course, provided that the increasing property of the stack is maintained. So in this way, we can describe our optimal sorting algorithm. That is, always try to push the elements of the input into the stack. If you can do it without losing the increasing property of the stack, then just do it. Otherwise, pop the stack. We can do it for our permutation here. And of course, as we have already observed, at the end, we don't get the identity, but at least we get an output. So we have defined this sorting algorithm, which is usually called stack sort. And what do we know about stack sort? Well, we know essentially everything, even if there are still some things that are not completely understood. Anyway, we have a complete characterization of sortable permutations in terms of the avoidance of a single pattern of length 3, and we know that they are enumerated by Catalan numbers. We have an optimal sorting algorithm, which is stack sort. But for instance, we don't have a complete understanding of the preimages of the stack sort operator. There are many interesting results concerning this, but still many things are not clear. And this appears to be a not so easy problem. At any rate, the results we have on sorting permutations with a single stack are very nice and very neat. And so it is natural to try to extend them to more complicated situations, more complicated machines. And in fact, right after these results for stack sort, many people started investigating the same kind of question for more complicated network of devices. And here in this slide, I have listed some of the results that have been obtained. Some of them are interesting properties regarding machines consisting of stacks or queues or other containers connected in series or in parallel maybe. But very soon people realized that it was very difficult to analyze these very general machines. And it became soon clear that these were very difficult problems even when dealing with small networks. So many people started to look at one specific case, which is indeed one of the smallest networks that one can conceive. That is the case of two stacks connected in series. Well, as a matter of fact, at present, this case is still open in its full generality. And we know only a few things on this sorting machine. For instance, we know that sortable permutations are a class having an infinite basis. This is due to Murphy. We have no idea about the enumeration of sortable permutations. We just have some kind of asymptotic results, most recent one by L.V. Price and Gutmann and Defant also. We also do not know of any optimal sorting algorithm. From the algorithmic point of view, probably the most interesting thing that we know is that there is a polynomial procedure that tells us if a given permutation is sortable or not, due to Pierrot and Rossin. Again, since this appears to be a very difficult problem in its full generality, it is natural to consider some more specific situations. Typically, two things that can be done are to choose a specific algorithm and or to impose some kind of constraints on the content of the stacks, meaning that at each step of the sorting procedure, the content of the stacks has to obey some sort of condition. So several special cases have been considered, and here and in the next slides, I have recorded some of these special cases. I don't claim to be exhaustive here. I've listed some of the several special cases that have been considered, some of the most famous ones, and maybe some that I have found particularly interesting. So one of the most classical and known special cases is the so-called West two-stack sorting. That is essentially making two passes from a classical increasing stack. This is nothing else than performing stack sort twice on an input permutation, or equivalently to deal with the two stacks in series using a kind of right greedy algorithm. We know a lot of things in this case. We have a characterization of sortable permutations in terms of Barrett patterns, and we have the enumeration of sortable permutations, originally due to Zeilberger, and then rediscovered in a more bijective fashion. In fact, a lot of interesting bijective combinatorics is connected with this case, and there are many remarkable combinatorial objects that are in bijection with sortable permutations, such as non-separable planar maps and left ternary trees, generalized Tamari intervals, fighting fish. There is also an extension to the case of three stacks in series due to Ulfarson and Clesson and Ulfarson. A generalization of the case considered by West is to have, again, two increasing stacks in series, but this time without fixing a specific algorithm. This case was considered and completely solved by Atkinson, Murphy, and Raskak, and there are also some funny results in this case. For instance, sortable permutations are a class with infinite basis, but they are counted by a sequence which also counts permutation avoiding a single pattern of length 4. This is probably the first example of a so-called unbalanced Wilf equivalence, that is, two classes of permutations which are equinumerous, but are defined in terms of two bases having different cardinalities. And, well, this is a case of an extremely unbalanced Wilf equivalence, since in one case the basis has only one element, and in the other case the basis is infinite. Then one can consider pop stacks in series rather than two stacks. A pop stack is like a stack, but now when we want to pop elements from the stack, we cannot pop them one at a time, but we are required to empty the whole stack. Also in this case, considered by Avis and Newborn, we have rather complete results, as well as in the more specific case of 2 passes from a pop stack, considered actually much later by Lara Pudwell and Rebecca Smith. And here we also have a generalization to k passes from a pop stack due to Claesson and Gudmundsson. Somehow mixing the previous special cases, another interesting device consists in taking a stack and a pop stack in series. This was considered by Rebecca Smith and Vince Vater, and there are interesting results also in this case concerning characterization and enumeration of sortable permutations. Now, in order to illustrate my first result, I will consider one more special case of the 2 stacks in series problem, consisting of having a decreasing stack followed by an increasing stack. This situation has been studied by Rebecca Smith, and she has been able to provide a complete analysis of this sorting machine. So here the possible operations are obviously 3, mu1, mu2, and mu3. And for this machine, there is an optimal sorting algorithm due to Rebecca that I will now describe, and also characterization and enumeration of sortable permutation. The algorithm works as follows. The first thing that you try is to see if you can perform mu3, in case the top of the increasing stack is the next element to output, of course. If this is not the case, you try to perform u1. And in order to perform u1, you have to check these 2 inequalities. The first inequality is obvious because d is a decreasing stack, so what you put at the top of this decreasing stack has to be larger than the actual top of the decreasing stack. The other inequality is slightly less obvious but reasonable. Okay, if you cannot perform u1, then you try to perform u2, and in this case you just have a trivial inequality to satisfy because I has to be an increasing stack. And finally, if you cannot perform any one of these operations, then you just perform u3, and this is the case in which the output permutation won't be the identity permutation. Okay, using this algorithm, it is then possible to prove that sortable permutations constitute a class whose basis consists of 2 permutations of rank 4, and it turns out that the enumeration of this class of pattern avoiding permutations is known, and it is given essentially by the Schroeder numbers. Now, looking at these results, it is reasonable and somehow natural to compare this DI machine with the single stack machine. Indeed, as it is shown in this table, in both cases, sortable permutations are a class having, say, a small basis of small permutations. For the single stack, 1 element of length 3, and for the DI machine, 2 elements of length 4. So they are kind of comparable classes. Also, the enumeration of sortable permutations is given by 2 number sequences that are very similar from many points of views. For instance, in both cases, the generating function is algebraic of degree 2. And finally, for both machines, we have an optimal sorting algorithm. So, due to the similarities between a single stack and the DI machine, it is reasonable to at least ask what happens if we add 1 more decreasing stack in front. The idea is that maybe the resulting machine can show some similarities with the case of 2 stacks in series. So we can consider this DDI machine to see if this is true. So now we have 2 decreasing stacks followed by an increasing one. If we compare this machine with the 2 stacks in series, concerning the characterization of sortable permutations, okay, we already know that for the 2 stacks in series machine there is an infinite basis. And it is indeed possible to prove that the same happens for the DDI machine. So this is the first analogy. Moreover, there is a strict analogy also for what concerns the enumeration of sortable permutation, since we simply don't know in both cases how many they are. Instead, there is a major difference concerning the existence of an optimal sorting algorithm. In fact, there is no known optimal sorting algorithm for the general 2 stacks in series problem, whereas we are able to describe one such optimal sorting algorithm for the DDI machine. And this will be the first result that I would like to illustrate in my talk. First, very quickly, here is a slide with a theorem that records the fact that sortable permutations in the DDI case have an infinite basis. As usual in these proofs, we don't actually find the real basis, but we just find an infinite antichain of basis permutations, which are these alpha j's here. And as you can see, these basis permutations are essentially so-called decreasing oscillations. They have a prefix having 2 fixed elements, actually the first depends on j, then a suffix of 3 fixed elements, and there is a middle part here, which is this decreasing oscillation, as can be seen also by this picture here at the bottom of the slide. This is, however, a result that we already presented at Dartmouth 3 years ago, so I won't spend more time on this. Instead, I will now give you a somewhat detailed description of our optimal sorting algorithm. So now we have 4 possible operations, of course, mu0, mu1, mu2, and mu3. And in order to better understand our algorithm, the idea here is that our algorithm is a kind of extension of Rebecca's one for the DI machine, where now the role of the input in the DI case is played in some sense by the content of the decreasing stack. So in this sense, the operations mu1, mu2, and mu3 behave similarly to the corresponding operations of the DI machine. And the conditions to satisfy in order to perform each of them is similar to the analogous condition for the DI case. Instead, here the new operation is this operation mu0 here, and as we will see, the condition to be satisfied in order to perform mu0 is sensibly different from the other ones. It does not simply consist of verifying some inequalities, but there is also a more complicated fact to check, for which one has to look somehow deeper inside the input. Anyway, here is the algorithm. The first thing that you try, as usual, is to perform mu3 in case the top of the increasing stack is the next element to output, of course. If this is not the case, the next try is to perform mu1. And in order to perform mu1, again, you have 2 inequalities to satisfy, which are completely analogous to the inequalities for the same operation in the DI case. If you cannot perform mu1, you see if you can perform mu0, which is the new operation. And in this case, again, you have 2 inequalities to satisfy. This is obvious, and this is anyway reasonable, but there is also another condition to be satisfied, which is the following. You have to look at the sequence starting from the current element in the input up to the first element of the input, which is larger than the top of D2. Well, if this sequence is increasing, then you can perform mu0, otherwise you cannot. Okay, supposing that you cannot perform mu0, you try to perform mu2, and in order to do this, you have just to check this trivial inequality. This is trivial because I is an increasing stack, and otherwise, if you cannot perform any of these operations, you just perform mu3, and this is the case in which you get a permutation which is not the identity permutation. Okay, here is our algorithm, and here is an example of how this algorithm works on a permutation, which in this case is a sortable permutation. Of course, I won't describe each single step of the execution, just a couple of them, which are maybe interesting because they concerns the execution of this new operation mu0. So for instance, consider this case here. There are 2 possibilities. You can perform either mu0 or mu2. The first try is with mu0, and indeed you can perform mu0 because, well, first of all, these 2 inequalities are vacuously satisfied because D1 and I are both empty. So we assume that in this case these inequalities are satisfied. And next you have to check that the sequence of elements starting from 4 to the first element of the input larger than 3, which is again 4. So in this case, this sequence consists of the singleton of 4. Well, this has to be increasing, and of course this is increasing. So you can perform mu0. Another interesting case is the following. Again, you have 2 possibilities, either performing mu0 or mu2. Again, you start by checking if you can perform mu0. Again, these 2 inequalities are vacuously satisfied, and it turns out that now you have to check this prefix of the input. You take all the elements starting from 1 to the first element larger than 4. So in this case, this is the sequence 1, 9. It is increasing, so you can perform mu0. Finally, one more interesting case is this one. In this case, there are 3 possible operations. You can perform either mu0 or mu1 or mu2. But in this case, you cannot perform mu1 because, for instance, the top of D1, which is 1, is not bigger than the top of D2, which is 9. So you cannot perform mu1, but you cannot perform mu0 too, because if you look at the sequence of elements starting from 6 and terminating to the first element of the input larger than 9, well, 9 is the maximum here, so you have to take all the remaining elements in the input, and this sequence is not increasing, so you cannot perform mu0. Next try is to perform mu2, and luckily you can perform mu2 because the top of D2, which is 9, here is smaller than the top of I because I is empty. And okay, if you continue the execution of this algorithm till the end, you will get the identity permutation. So I think that this algorithm is rather interesting, first of all because it extends Rebecca's one for the DI machine, and also because it may help in, I guess, in tackling the general two stacks in series problem. For instance, it would be interesting to exploit this algorithm to enumerate permutations sortable with the DDI machine. We have made no attempt in this direction for the moment, but having an optimal sorting algorithm often helps to count sortable permutation. And well, if we believe that there is some analogy between the DDI machine and the two stacks in series machine, solving this counting problem for the DDI machine may give at least some hint on the proportion of sortable permutation also in the two stacks in series case. Finally, one could ask what happens by adding more decreasing stacks in front, so to have a, say, d to the ki machine. What kind of conditions do we need to check in order to perform the various operations? Okay, so this was the first result I wanted to illustrate in my talk. Now, the second result, as I promised, is the introduction of a new family of sorting machine, for which I'll try to address the problem of characterizing and enumerating sortable permutations. Let's start by considering again the well-known west-to-stack sorting problem algorithm. Again, this consists in two passes from a classical increasing stack. This is the meaning of this I at the bottom of each stack here. The fact that the stack is increasing can also be equivalently expressed by saying that its content has to avoid the pattern 2-1 from top to bottom. So a natural generalization that comes to mind is to impose that during the first pass, the content of the stack has to avoid a certain pattern sigma. Of course, during the second pass, the stack is required to still avoid 2-1 in order to have some chance to get the identity permutation as output. This gives rise to a new family of sorting machines in which we make two passes from a stack and impose that during the first pass, the stack is sigma avoiding from top to bottom, and during the second pass, the stack is 2-1 avoiding. We thus have an algorithm that we will call the sigma stack sorting algorithm. This machine is the sigma machine, and the set of permutations that are sortable using this device are called the sigma sortable permutations. My motivations for considering these sigma machines, well, comes from an attempt to gain a better understanding of the general two stacks in series problem, as usual. Also, it could be the case that this sorting algorithm may help in finding some sorting algorithm for the general case. For instance, it would be nice to have some kind of result saying that a permutation is sortable by two stacks in series if and only if it is sortable by some sigma machine for sigma belonging to a certain set of patterns. This is probably rather hopeless, but it may be worth a try at least. One more motivation, which I hope to show you now, is a really good motivation, is that the study of these sigma machines gives rise to some very nice and enumerative bijective combinatorics. So what I will do now is to investigate sigma sortable permutations, trying to characterize and enumerate them. We start from very small patterns, so suppose that the length of sigma is 2, thus we have two cases. When sigma is the reverse identity to 1, then we get exactly West machine, whose sortable permutations are totally understood. In particular, remember that they can be characterized in terms of a classical pattern and the Barth pattern, and so they are not a class. Instead, if sigma is the identity 1, 2, we have a decreasing stack followed by an increasing 1. So this is a situation very similar to Rebecca's DI machine, but now we are fixing a specific algorithm. We first make a complete pass through the decreasing stack, then a pass through an increasing stack. So this is a less powerful device. And it is easy to see that sortable permutations are exactly 2-1-3 avoiding permutations, which are a class, by the way. Now, looking only at these very small and easy cases, there is already one interesting thing that can be observed. We have two cases here. And in one case, sortable permutations are not a class, whereas in the other case, they are. This suggests an additional intriguing question. That is, for what sigma do we get classes? Well, if you look at patterns of length 3, we realize quite easily that there is the pattern 3-1, for which 3-1 sortable permutations are a class. However, in the 5 remaining cases, sortable permutations are not a class. In this table, for each of the 5 remaining patterns, you can see one sortable permutation together with a sub-permutation which is not sortable. So, for patterns of length 3, we have 5 cases in which we do not get a class. Looking at longer patterns, we see that For patterns of length 4, there are 14 non-classes. For length 5, 42 non-classes. For length 6, 132 non-classes. Well, this cannot be a coincidence. These are Catalan numbers. And in the next slide, I will show you why this is true. I just need one simple notation. For any permutation sigma, denote with sigma head the permutation obtained from sigma by swapping its first two elements. Now here is the theorem. The set of sigma sortable permutation, denoted by sort sigma, is not a class if and only if sigma head avoids 2, 3, 1. An immediate corollary, an immediate consequence of this theorem is that the set of those permutations sigma for which sort sigma is not a class is counted by Catalan numbers. Okay, so this theorem tells us everything about known classes. Let's see what happens when we instead get classes, which is the next theorem. So, if sigma is such that sort sigma is a class, which as a consequence of the previous theorem means that sigma head contains 2, 3, 1, then the class, in this case of sigma sortable permutation, is a subclass of the class of 1, 3, 2 avoiding permutation. And it is precisely the subclass of those 1, 3, 2 avoiding permutations, also avoiding the reverse of sigma. In general, this is a proper subclass of 1, 3, 2 avoiding permutation unless 1, 3, 2 is a pattern of sigma reverse. Okay. I'd like also to mention an interesting open problem here, which we haven't actually considered yet. The problem is that of providing a classification of sigma machines, so the pattern sigma, in terms of the number of sigma sortable permutations. Well, it may happen that for different sigma, one gets the same number of sortable permutations, so it would be interesting to investigate this notion of kind of Wilf equivalence for sigma machines. Okay, next I would like to give you some details on the cases that we have been able to solve completely. Here we consider patterns of length 3. There are, of course, 6 cases, and for 3 of them we have complete results, whereas the remaining 3 are still open. The simplest case is for 3 to 1 sortable permutation, which are counted by the powers of 2, and there's a bijective link in this case with dig path of height at most 2. In the case of 1, 2, 3 sortable permutation, this is the counting sequence, and there is a bijective link with a certain class of pattern avoiding Schroeder paths. And finally, for 1, 3, 2 sortable permutation, the counting sequence is this binomial transform of Catalan numbers, and in this case the bijection is with a class of pattern avoiding restricted growth functions. So the link here is with set partitions. The 3 patterns which are still open are 2, 1, 3 and 2, 3, 1. In these cases, for the associated sortable permutation, we just have the first term of the corresponding counting sequences, which are not in the OEIS. And concerning 3, 1, 2 sortable permutation, these are the first term of the associated counting sequence, which appears in the OEIS as sequence A202062, which counts ascent sequences avoiding 2, 0, 1. But for this sequence, there is no closed formula, no formula in general. So it would be really interesting to find the bijection between 3, 1, 2 sortable permutations and ascent sequences avoiding 2, 0, 1. Okay. Now a few more details for each of the solved cases. So concerning the 3 to 1 sorting machine, here what we need is one version of a very well-known bijection between dig paths and permutations avoiding a pattern of length 3. This bijection is slightly different depending on the pattern to be avoided. Here we need permutation avoiding 1, 3, 2 because remember 3 to 1 sortable permutations are a class, and so they are a subclass of permutations avoiding 1, 3, 2. So we need here this bijection between dig path and 1, 3, 2 avoiding permutation, which can be described as follows. Take your dig path and label the up steps of your dig path from right to left increasingly, and then label also the down steps of the dig path in such a way that each down step has the same label of the up step it is matched with. And then you can read your permutation by reading from left to right labels of the down steps. Okay? Now remember that 3 to 1 sortable permutations are the class of permutations avoiding 1, 3, 2 and 1, 2, 3. So now we have to read this 1, 2, 3 restriction using this bijection inside the class of dig paths, and it turns out that this restriction can be read inside dig paths by saying that this is the class of dig paths of semi-length n and height at most 2. Finally, this class of permutations avoiding 2 patterns has a known enumeration which is given by these powers of 2. Okay, now let's see what happens with 1, 2, 3 sortable permutations. This is a much more challenging case, and we will count the sortable permutations by giving a bijection with a certain class of pattern-avoiding Schroeder paths. Well, we also have a formal analytic proof, but the bijective link with Schroeder paths is probably more beautiful. So start with the permutation, this pi here of length n, here n is 9, and decompose it into a prefix and a suffix. The prefix is this L here, which is the initial sequence of consecutive ascents of pi deprived of its last element. So in this case, this initial sequence of consecutive ascents is 5, 6, and 7. Just forget about 7, and your L is just 5 and 6. Suppose that the length of L is R, in this case R is equal to 2, and W is the suffix of the remaining element. Now let's focus on W. Inside W, consider the first element of W, and now consider all the elements of W which are larger than its first element. So these green elements here. It is possible to prove that these elements appear consecutively inside omega. Suppose that you have S of this green element, which are 2 in this case, and remove them, and consider the permutation rho, which is obtained from W by removing the green elements and the rescaling if needed. I am aware that it is difficult to read this yellow rho permutation because of the yellow color, which is very light, but the reason is that we don't actually need this yellow permutation. Instead, we need this orange permutation, tau, which is obtained from rho by just removing this 7, the first element of the yellow permutation. Concerning this permutation tau, it is possible to prove that tau avoids the pattern 2, 1, 3. So, in order to describe our bijection with a certain class of Schroeder path, we will now proceed as follows. Consider inside the pi this orange permutation, and consider the Dick path which corresponds bijectively to this orange permutation. Now, in this case, this is a permutation avoiding 2, 1, 3, so we need a different version of the previous bijection, which labels the step of the Dick path in a different way, but anyway, doesn't matter. So take the Dick path associated with this orange permutation and complete your Schroeder path by adding a prefix of horizontal step and the suffix of horizontal steps. The number of horizontal steps here in the prefix is given by the length of L, so 2 in this case, and the number of horizontal steps in the suffix here is given by the number of green elements here, which is again 2. This is a bijection between 1, 2, 3 sortable permutations and a certain class of Schroeder paths, and it is not difficult to see that this is precisely the class of Schroeder paths avoiding the pattern UHD. In this case, avoidance has to be intended as non-contiguous pattern avoidance, which means that these are Schroeder paths in which you cannot find any 3 steps, such that the first one is a U, the second one is an H, and the third one is a D. The semi-length of the Schroeder path is n-1 because of these elements removed here. So in order to count 1, 2, 3 sortable permutation, you can count this class of Schroeder paths, and it is not extremely difficult to do it, because if this is the associated generating function, well, one of these Schroeder paths can either be the Schroeder path consisting only of horizontal steps, which is counted by this piece of the generating function, or there can be a non-empty Dick path here in the middle. And in this case, you have to choose a prefix of horizontal steps here, which is counted by this, a suffix of horizontal steps, which is counted by this, and then you can put a Dick path here in the middle, which is non-empty, and this x here takes into account the fact that you have removed this element. So you get this generating function, and the nth coefficient of the generating function is, as it is possible to prove, given by the partial sums of Catalan numbers minus n. Okay, concerning the third case, 1, 3, 2 sortable permutations, we have this theorem which says that the set of 1, 3, 2 sortable permutations can be characterized in terms of these two, of the avoidance of these two patterns, one classical pattern, 2, 3, 1, 4, and this mesh pattern mu, which is this mesh pattern here. Concerning the enumeration of 1, 3, 2 sortable permutation, well, what you have to do is to consider the decomposition of a permutation in terms of its left to right minima. So here is this decomposition that you can consider for any permutation. Then when you have a permutation which is decomposed in terms of its left to right minima, you can associate with it a set partition. The most obvious way to do it is to consider elements in between two consecutive left to right minima, but it turns out that in this case this doesn't work, and instead you have to consider the set partition whose blocks are the horizontal strips here, this hi. So this defines a map from permutations to set partitions, or restricted growth functions, if you prefer. And it turns out that if you restrict this map to 132 sortable permutation, this is a bijection between 132 sortable permutations and restricted growth function avoiding this specific pattern. And there's a paper by Jelinek and Mansour which counts this set of pattern avoiding restricted growth function, and the counting sequence is given by this binomial transform of Catalan numbers. Okay, just a couple of words concerning possible further work on sigma sorting. One possibility is to extend the case of sigma machine by passing from the case of avoiding a single pattern during the first pass to avoiding a set of patterns during the first pass. If you do this in the case of just two patterns, several cases have already been solved by Barilcher, by Khalil and Wajnowski. Another line of research is to characterize sorted permutations and to investigate fertility. This is, was considered by Berlow and Defant and Zheng. And another problem is to replace permutations with more general words, so to consider sigma sorting machine on words that can be unrestricted words or Cayley permutations or ascent sequences or maybe other possibilities. And anyway, many more open problems and further works can be found in Giulio Cerbai's PhD thesis. Okay, so now I come to the third and final result that I would like to present today. As I promised, this is something concerning the study of preimages under a certain sorting map. So the sorting operator that we will now consider is what we obtained from the classical stack sort algorithm by replacing the stack with a queue. What happens if we do it? Well, it happens that we obtain a not very interesting algorithm, because in this case the only sortable permutations would be the identity permutations. However, if we allow one more operation, which is the bypass of the queue, we in fact obtain a rather interesting sorting algorithm, which is usually called Q-sort. So here is how this algorithm works. Consider the current element in the input permutation. You compare it with the element which is in the back of the queue. If the current element of the input is larger than the element in the back of the queue, you just enqueue it. Otherwise, you compare the current element in the input with the element in the front of the queue, and you just output the smaller one. Okay, this algorithm is, well, we know many things concerning this algorithm. For instance, we know that sortable permutations are precisely 3-to-1 avoiding permutations, so we know that they are enumerated by Catalan numbers. But, for instance, what can be interesting to investigate is preimages under this Q-sort operator. Well, the study of preimages under the stack sort operator is a now classical problem that began with a paper by Bousquet-Melou and recently has received a lot of attention by Colin Defant and other people. There are lots of papers on it. And, well, it is a rather difficult problem. So it is difficult to obtain results. There are many interesting results, but they are not easy to obtain, and there is still much that remains unknown. Instead, for the Q-sort sorting operator, the same problem had not been considered before. But, well, the Q-sort sorting operator is somehow simpler than the stack sort operator. So hopefully it is reasonable to think that more results can be obtained, and maybe neater result. In the next slides, I will describe what we know on the combinatorics of preimages under Q-sort. All the results that I'm going to show have been obtained in collaboration with La Poccioni. So the first thing that we need is an alternative but equivalent description of Q-sort which acts directly on permutations without any reference to the Q. So consider an input permutation like this and consider the decomposition of the permutations in terms of its left to right maxima this time, which are the red elements here. So this algorithm works as follows. Consider the left to right maxima from right to left. So take the rightmost left to right maxima and move it to the right until it hits some larger element. So of course, during this first step, you are considering the rightmost left to right maxima, which is the maximum of your permutation. So of course, this element just reaches the last position in the permutation. Then continue and do the same thing for the next left to right maxima from right to left, so the second to last left to right maxima, which is this 2 here. So move it to the right until it hits a larger element, so in this case you move these 2 up to this position, and of course continue now with all the remaining left to right maxima from right to left. At the end, what you will get is a permutation which is the same output of the Q-sort algorithm. An immediate corollary of this alternative description of Q-sort is that the set of permutations having non-empty preimage is precisely the set of permutations ending with the maximum element. Okay, using this description of Q-sort, we can obtain our first result, which is a recursive characterization of preimages of any permutation pi. So what we will describe now is a recursive algorithm which is able to generate all the preimages of a given pi. In order to do this, we need to consider the usual decomposition of pi in terms of its left to right maxima, and we also want to collect together contiguous left to right maxima. So we consider this decomposition of pi that we have called LTR max decomposition of pi as M1, P1, M2, and P2, and so on, where the MIs are the maximal sequences of contiguous left to right maxima of pi. So for instance, in this permutation, the first 2 elements are left to right maxima, so this is M1. The third and fourth element are not LTR maxima, so this is P2. Then you have again 3 elements, 6, 8, and 9, which are left to right maxima, so this is M2. Then 7 and 4 are P2, and so on. Now observe that as a consequence of this definition, each of the Pi is necessarily non-empty, and the same holds for each of the Mi, except at most for the last one, which is non-empty precisely when the permutation pi ends with its maximum. So in this case, this permutation doesn't end with the maximum, so in this case, M3 is empty. Just a couple of very quick notation. For any string alpha, I will denote with alpha dash the string obtained from alpha by removing the last element, and also I will denote with mu I the last element of each of the Mi, which is also the largest element because the Mi are increasing. So here is the algorithm. Take pi and consider its decomposition, LTR max decomposition. If pi is the identity permutation, well, of course, preimages of pi are 3 to 1 avoiding permutations. Otherwise, you have 2 types of preimages. Concerning the first type, you remove from pi the element starting from mu k minus 1, the last element of the second to last sequence of left to right maxima, up to the end of the permutation, except for the very last element, which is n. So remove these elements here, consider this permutation after rescaling, and compute all the preimages of this permutation, and concatenate each of these preimages with this string here. The second type of preimages occurs only when the suffix of left to right maxima has at least 2 elements. In this case, you just take pi dash, removing the last element. You compute all the preimages of pi dash. This is the generic one, and you insert again n in each of these preimages, in each of the positions to the right of ns minus 1. So from here, in each of the positions here. Here is an example of how this algorithm works. Consider this permutation here, 2, 3, 1, 4, 5. In this case, we have a suffix having 2 elements, so both cases here occurs. In the first case, you have to remove this string 3, 1, 4 here, and you have to compute the preimages of 2, 5, which are 2, 5, and 5, 2, and then you have to concatenate with 3, 1, 4, thus getting these 2 preimages. For the second kind of preimages, you just remove the 5, so you have 2, 3, 1, 4. And now we have to compute preimages of 2, 3, 1, 4. And of course, you do it by recursively using again this algorithm. In this case, the suffix of left-right maxima has cardinality 1, so only this kind of preimages occur. And to compute them, you have to remove this string 3, 1. So we are left with 2, 4. You compute the preimages of 2, 4, which are these two, and you concatenate with 3, 1. Thus obtaining these two preimages of this permutation. Now you have to insert 5 in each of the position to the right of the orange element. So in this case, you obtain these 3 permutations, and in this case, you obtain these 4 permutations here. And so this is the whole set of preimages of these permutations. Okay, using this recursive characterization of preimages, we can give some interesting results concerning preimages. First result concerns an answer to this question: how many permutations are there having a given number of preimages? So we are interested in these sets Q and K of all permutations pi of length n, such that the number of preimages of pi is equal to k. We are interested both in characterizing permutations in the set and enumerating them. Well, we already know that when k is equal to 0, the number of permutations having no preimages is precisely the set of permutations not ending with the maximum, and it is easy to count them. So what happens for other values of k? Well, when k is equal to 1, the set of permutations having precisely one preimage is the set of permutations ending with the maximum, and such that there are no two adjacent left-right maxima. And we can count them using the classical Foucault fundamental bijection, which maps permutations in one-line notations to permutations in cycle notation. So we'll find that the number of these permutations is given essentially by these derangement numbers. In the case k equal 2, the set of permutations having exactly two preimages is a set of permutations ending with n, and such that the only adjacent left-right maxima are the first two elements of the permutation. Also in this case, we have complete enumeration, which is obtained from this recurrence here with this initial condition. We also have a link with the previous counting sequence, and we have this exponential generating function. Okay, what about larger values of k? So up to now, we know that when k is equal to 0, 1, and 2, well, we know that there are permutations having 0, 1, or 2 preimages. We also have this proposition which says that if pi is this specific permutation of length n plus 4, then this permutation has precisely n plus 2 preimages. And this holds for n greater than or equal to 2. So this means that every natural number starting from 4 is an allowed cardinality for the number of preimages of some permutations. So there are permutations having n preimages for every n greater than 4. Together with what we already know, that is, there are permutations having any possible cardinalities, having cardinalities 0, 1, or 2. We thus have that every natural number is an allowed cardinality for the number of preimages except for 3. And in fact, we have this proposition which tells us that there exist no permutations pi such that the number of preimages is equal to 3. And this is a nice and rather striking result, since it says that all natural numbers are allowed cardinalities for the number of preimages except for 3. Okay, my last result is an answer to the following question: how many preimages do a given permutation have? So the easiest case is when pi is an increasing permutation, so the identity, and in this case we know that the number of preimages is given by a Catalan number. The next case is to consider permutation pi such that there is a prefix, non-empty prefix of course, of left to right maxima. There is a non-empty suffix of left to right maxima, and there is also a middle part here, non-empty too, consisting of elements which are not left to right maxima. So in this case, the number of preimages is given by this double summation, in which there is a binomial coefficient and there is this product of ballot numbers. We can somehow simplify this expression by introducing Catalan numbers, which are sums of ballot numbers, and if you do this, we get this equivalent expression which has just one summation, and which is essentially a linear combination of Catalan numbers whose coefficients are polynomials in P1, where this P1 is the number of elements in this big P1 here. Some special cases can be obtained by choosing as small numbers for the cardinalities of M2. So when M2 has cardinality 1, 2, or 3, here are the number of preimages of pi. As can be noticed in these linear combinations of Catalan numbers, the coefficients seems to somehow stabilize, and this may be not too hard to prove. We have not tried to do actually. And okay, just to mention that there can be many interesting open problems concerning again the Q-sort map, but also other maps associated to other sorting operators. For instance, let me mention just this final problem, which is studying preimages of maps associated with other sorting algorithms. One possibility is to consider C machines, which actually are generating machines, but of course when one can consider the associated sorting counterpart. This is a suggestion due to Winsvater. Or maybe one can consider the bubble sorting operator, and this is work in progress with Lapo and Mathilde Bouvel, or maybe other sorting operators. Okay, this was my last slide. Thank you very much for listening, and most importantly, see you in person next year. Thanks.